残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には遥か未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
Yeah, sir, I'm gonna need you to open up the window there. Yep. You been doing any calculus tonight? Yeah, don't lie to me. Don't lie to me, I can see the integrals right there on the driver's seat. Okay, what's up guys? We're back talking about section 5.1, which is all about approximating the areas under curves. So the basic gist of it is that the derivative of a function is associated with rates of change and the slopes of tangent lines. The slopes of tangent lines, this is telling us some sort of geometric information. This is telling us something about what's going on in the way that the function is broken down into smaller pieces, in some sense. We also know that antiderivatives, or indefinite integrals as we've started to call them, they reverse the derivative operation. It undoes a derivative. And this raises a big question. This raises a fundamentally important question to us. What is the geometric meaning of the integral? This is a big question. Now, for one, I want to say that there's not necessarily any reason that this has to have any particularly good geometric meaning. The thing that suggests it might is that the derivative carries geometric meaning. So since this is just undoing the derivative, perhaps some of the geometric meaning conveyed in the derivative is carried over into the indefinite integral, or is preserved by it, or is recovered, or is just still there somehow. So to answer this question, let's start out with an example. Let's imagine a car traveling at a constant velocity of 60 miles an hour along a straight highway over a 2-hour period. So just imagine you're in a car, you're driving at 60 miles an hour, and you drive for 2 hours. The graph of the velocity function, which is just v equals 60, how fast you're going, on the interval from 0 to 2, for t, the time variable, between 0 and 2 hours, is just a horizontal line. Let's look at a picture. So here we go. Here's a picture of what's going on. So we've got our velocity function, we've got the time in hours, half an hour, 1 hour, an hour and a half, 2 hours. Everywhere on here, we're just going 60 miles an hour. This is constant. Okay, so 60 miles an hour, this is how fast we're going. We drive for 2 hours. Notice something. The displacement of the car, how far we've traveled in total, is found by a familiar formula. We can just go, oh, how far did I drive in total? Well, how fast was I going and how long did I drive? It's rate times time. So 60 miles per hour times 2 hours, you can see it like those hours are canceling out and you just get 60 times 2 miles. 120 miles is how far I went. Now, let's notice something. All right, jump into a different screen here. The thing we're going to want to notice is that when we look at this graph of the velocity function here, notice something cool. We went 120 miles in total. Yeah, we went 120 miles in total. The area of this rectangle here, the product here, this area between 0 and 2 hours and under the graph of the velocity function has an area that is equal to the displacement of your vehicle. That is, if you graph the velocity function, then the area of the rectangle here underneath that graph tells you how far you went over the entire 2 hours. This is kind of neat. I bet when you think about how far you went during a trip, you're not really thinking about areas. It doesn't seem like you're calculating the area of a rectangle. But in some kind of fundamental way, you are. You're multiplying two things together. Areas are two numbers multiplied together. So when you have a constant positive velocity, we'll see that the area between the velocity curve and the t-axis, the time axis, is the displacement of the moving object. The displacement is the area. So for 2 hours of elapsed time and 60 miles per hour of velocity, notice when you multiply them together, you're getting the area of this box here. And this is the observation that will lead us to our geometric intuition for the indefinite integral. Let's talk about it. Okay, so in the context of our example here, let's notice something. Since v, which is really a function of t, we've been writing it as v equals 60 miles per hour, but really it's a function of time. It's just the same at every time. So really, if you want, you could write it as, v of t if you felt like it. It's a function of the time variable. At a given point in time, you're traveling at a certain velocity, v of t. Okay, cool. So if we take the indefinite integral of v, what we get is just, well, let's just run through it. Take the integral of v dt. So v is just this function right here, this constant function of 60. We're just integrating 60 dt. And from this, we'll get out 60t plus a constant. So up to a constant, this is what we get back. Now, think about this. The derivative, as we've learned before, of a position yields velocity. So this is the position function. Up to a constant, that is. That constant plus c right there matters a little bit. What this is saying is that it doesn't matter where you start in terms of velocity. Velocity doesn't pick up your starting point. It just picks up how fast you're going. Maybe you call your starting point 0. Maybe you call it 2. It doesn't matter, because after you started, velocity is just picking up how fast you're going. So this is your position, kind of. If you watched the video we did last time, the bonus math video about initial value problems, this is exactly the same thing that's going on there. So we've got a differential equation, essentially. You don't need to know about that for this right here, but basically we've been given information about velocity. We've been given information about the derivative of position. What we get back right here is the position up to a constant. To know what that constant is, we need a little bit more information. So let's call this function p of t. That is, let's let p of t be given by 60t plus a constant. Okay, now we can observe that at the time t equals 0 hours, the position is p of 0 equals c miles. That is, just plug in 0, and we'll get 60 times 0 plus c, and anything times 0 is 0, so this is just c. Okay, so p of 0 is c miles. and at time t equals 2 hours, the position is given by p of 2, which if we just run through it, just plug in 2. That's 60 times 2 plus c miles, which is just 120 plus c miles. So what I'm trying to say here is that it doesn't matter what the value of c is for all intents and purposes as far as velocity is concerned or as far as displacement is concerned. As far as how far you went, it doesn't matter where you started. It just matters from wherever that point was, whatever you labeled the starting line, to whatever you labeled the ending line, how far was that? So regardless of the value of c, we can see that if I take p of 2 minus p of 0, I'll get 120 plus c, that's p of 2, minus c, that's p of 0. And naturally, this comes equipped with the unit of miles, and this turns into 120 miles. That's our displacement. So in the case of a constant velocity function, we see that the integral of v gives us some sort of information about the net distance we've traveled, the displacement. There's a little bit of an extra step here. It's this part where we are subtracting things. You'll see this formula again. You'll see this type of stuff a lot more. But the basic gist of it is that when I'm calculating an indefinite integral, if I evaluate the result at the endpoints of my interval, I'm getting information about how far I went. I'm getting information about an area under a curve. And as it turns out, we can do all of this without the physical intuition of driving in a car. I mean, why not? It would be weird if we could solve problems about driving in a car, but not problems about other things. This is just for intuition. So let's try to make it a little more general, and let's see what we can find. So in our car example, we were dealing with a constant function. We were driving at 60 miles an hour for the entire time. Now, in real life, you're rarely going a constant speed. You might put it on cruise control, but there's wind. I don't know, you go up hills, you go down hills. You travel slightly different speeds. It would be really annoying if we couldn't actually deal with something as simple as this. So, since objects do not necessarily move at a constant velocity all the time, things can go faster or slower, we must extend these ideas to positive velocities that change over an interval of time before we go any further. So, this is just, instead of dealing with just a flat line, let's deal with curvy lines. But to start it off, we're going to keep everything simple and make sure that everything is still, let me throw a different color here, just for this little picture. We're going to still make everything be above the x-axis. So if I'm graphing these guys out, I'm going to assume that everything I'm dealing with is still having graphs like this. All the functions I'm looking at are doing stuff like this. They're all above the x-axis. I'm going to assume for now that we're dealing with positive velocities that change over an interval of time. So the output's positive, it's always above the x-axis, and it might change a little bit over time. We'll deal with things that aren't just constant. But we'll still keep our physical intuition of speed. Okay. So the first strategy we could employ, perhaps this seems like a reasonable one, is to divide the time interval into many smaller subintervals and approximate the velocity on each subinterval with a constant velocity. That is, if I can deal with the constant case, maybe I can deal with the non-constant case by just treating a non-constant function as pretty close to a bunch of little constant functions. That is, if I'm traveling at different speeds, it might be the case that over a pretty small time interval, it's close enough that I'm traveling a constant speed. That is, over a millisecond, I might change from 50.01 miles per hour to 50 miles per hour. But I might as well just approximate this with 50 miles per hour. That seems fair. I won't be too far off. So this is just this kind of idea. Let's see what this will look like. This strategy will produce only an approximation to the displacement. However, we can improve the approximation by using more and more little constant functions. Basically, let's just picture the following. So if I wanted to figure out what the area under, say, this curve right here is, I could draw some little boxes under there. I could go, okay, let's start with the right endpoint. I'll split it into 1, let me use some colors, 2, let's see, 3, and 4. 4 different little boxes right there. So 4 little intervals. I've taken this whole thing and I've split it up a little bit. There's 4 little pieces, or maybe if I want to be even easier, let's just make it 2 for the moment. Let's just start with 2. So I could just start with 2 pieces here, just like this. Split up that interval from, say, 0 to 8 into 2 pieces. Okay, one goes from 0 to 4, one goes from 4 to 8. Split it right down the middle. That's easy. I could try using 2 boxes to approximate the area under this curve. Use this box, and then use the little orange box right here. And as you'll notice, this isn't the perfect approximation by any means. Let's zoom in on it a little bit. So if I use this approximation, it's not perfect, but it's all right. If I look at what the actual area is, let me see if I can do this with a little bit of opacity. It'll be something like this guy here. So this is the actual area, and as we can see, I'm picking up a little bit more than I need in some places. In fact, in both places. So I have this this extra little chunk over here, and I have this extra little chunk down here. These two guys are what makes this an approximation. These are extra. So I get some extra chunks, but overall, it's not an impossibly bad approximation. It's just not that great because I only use 2 boxes. Ah, okay. So maybe I look at this and I go, all right, I kind of approximated it, but it's not perfect. Maybe I want it to be a little better. Maybe I use, I don't know, 3 boxes. So here I'm using this box, split it up into, or maybe let's try 4. How about 4? It's going to be a little bit hard to see a couple of these, but maybe I use this box, which is almost just on the ground right there. It's so low. Maybe I use this pink box. Oh, another one. Let's do an orange one here. And maybe I use a, I don't know, make a yellow one. How about that? Bam. So once again, I'm doing a better job, but I'm not doing a perfect job. Over here I had this extra, and I also had, I should highlight this too, I had a little bit missing. This part was missing. So I got some that's extra, and I have some that's missing. Here, I get the same thing again. Some extra, some missing. But notice, I'll get a little bit less of either one. So let me highlight our total area again. If I'm looking for the area under this curve, it's going to be this whole thing in here. And in this case, I'm getting a bit too much in a few places, and I'm getting a bit too little in a few others. So these guys right in there, those are going over the edge. Got a little bit down at that bottom too. Okay, so these guys, these are extra again. And I'm still missing a little bit too. In fact, I'm missing maybe a little bit more. Oh, I forgot to shade in a piece before. Oops. Here. Let me make sure I got that down, just so everything's super clear. There's another piece that's missing. Kind of hard to keep track of some of these sometimes, but we have some missing over here too. We got a little bit right there, we got a little bit up here, we got a little bit there, and we got a little bit up top. So we got a few pieces that are missing. But notice, if I took all these chunks that are missing and I just put them together, I think that it's fair to say that it looks like the amount that's missing and the amount that's extra has gone down a little bit. All of these little triangles have gotten a bit smaller. So this little chunk right here, this chunk here, and this chunk here, if you add up their areas, I think it's fair to say that it seems a little bit smaller than that one over there. Similarly, the pieces that are missing seem a little bit smaller too. This becomes really clear once we start doing a lot of them at once. So the missing pieces got smaller, as did the extra pieces. Okay, if we do even more, and I won't draw the whole boxes again, but let's try it with like 8 intervals and see what it looks like. It's a lot more. Okay, so just once again, same picture as before basically, just with more boxes. And I think at this point it's pretty safe to say that it looks like we're getting better and better approximations. Basically, what's going on here is no more complicated than the fact that your TV or your phone screen or your computer screen is made of little pixels, but you can still see things that look like a smooth curve just because there's enough of them. It's not really that crazy, you can take things that don't look like they should, things that are a little bit, have hard edges, and if you have a lot of little things with hard edges and they're small enough, you can make it look like they're rounded. Basically, the idea is that it doesn't have to be perfectly smooth, but you can get pretty dang close with what you got. So, I'm just highlighting the chunks that are missing and the chunks that are extra. And as you can see, over time, it looks like we're sort of getting closer and closer to a pretty good approximation. I just went from, 2 to 4 to 8 intervals. And by 8, this is pretty good. So, the same way when we were dealing with the derivative, we approximated the slope of the tangent line with secant lines, and we defined the derivative in terms of the limit of that approximation. We're going to do the exact same thing when it comes to integrals. We're going to approximate an area under a curve, and we're going to take the limit of these approximations. Unfortunately, unlike derivatives, this will turn out to be a lot more of an involved process. Let's start to talk about the formalism here. So the idea is that in this case, I use the midpoint of each subinterval. I could have used other points. I could have split the intervals up in a lot of different ways. But at the end of the day, if I'm doing better and better approximations, eventually I'll get pretty close to the right thing. Let's define something that will let us talk about these approximations that we could take in a very general way. Let's cover all of them at once, make our lives easy so we don't have to talk about every case separately. Cool, let's get into it. So as you may have noticed when we were drawing all those boxes, we really stopped talking about displacement or velocity at all. So let's step back a moment and we'll get to the definition. Of course, we don't want to just spend all of our time talking about areas under curves. If the idea was only applied to computing displacements from velocity curves, there are a lot of functions. There are a lot of other things we could look at. There are a lot of ways that quantities can be related to each other than speed. So, as it turns out, the problem of finding areas under curves arises very frequently and turns out to be immediately important, as we will find out through the remainder of the course and in lots of other classes if you choose to take more calculus classes or other math classes. So, for this reason, we're going to develop a systematic method for approximating areas under curves. Any curves, or at least any nice enough curve, we'll talk about a way to approximate the area. These guys don't just have to correspond to velocity, but you should use your intuition from velocity to see that everything still makes sense when we're dealing with other quantities. It's kind of cool. You can sort of see the same things that you have physical intuition reflected in things that you might not have physical intuition for. So let's put the definition down in its full generality for area under any curve. Okay, so this is a little bit of a lengthy definition, and I want to involve you in the process of how we come about with all this weird formalism, otherwise it feels totally unmotivated. So, let's build up a common vocabulary so we can state this result in a way that's really understandable, this definition, this idea, in a way that makes sense. We'll need a vocabulary for this. So let's consider a function f that's continuous and non-negative on some closed interval from a to b. The goal we have here is to approximate the area of the region R bounded by the graph of f and the x-axis from x equals a to x equals b. That's just this picture right here. So this is the region R bounded by the graph of f and the f-axis from x equals a to x equals b. So taking a, I get out f of a, and taking b down here, I would trace up and I would get out f of b. And in between, I've got some kind of an area. So if I'm just thinking about this area between the x-axis and the graph of our function, this is what I'm looking at. Everything up to that top of that white line there, and everything down to the white line at the bottom, that's the x-axis. Okay, so here's my function. Here's what I'm looking at. And what I want to do is I want to approximate what this area is. So there's starting to be a little bit more formalism. We're talking about closed intervals, functions, a's and b's, f of a's, f of b's. And if you'll notice, there's pretty much no numbers at this point. That's going to be very common, so don't get freaked out by it. We're just giving labels to things so we can talk about them conveniently. So we're going to start by dividing the interval AB into n subintervals of equal length. We'll label these as x1, x0, x1, x1, x2, so on and so on up to xn minus 1, xn. Think of it like this. If I draw a number line down here, if I draw a little number line down here and I've got an A and I've got a B, then if I split this guy into two pieces, I would have x0, x1, and x2. One interval, this little guy right here, would be the interval from x0 to x1, and if I include the endpoints, I'll put square brackets on it. The other interval from x1 to x2 would be just exactly the same, but with x1 and x2 now. And if I include the endpoints, square brackets. So I've taken the interval from a to b, this guy down here, and I've turned it into two pieces. x0, x1, x1, x2. You can imagine that I could do this with more than two pieces. I could cut it at a couple of places. I could cut it unevenly. I could take an interval from a to b and I could cut it up in lots of silly and weird ways if I felt like it. So I could take a and b, and I could, let's use a different color. I could cut it here and there, and then I could do like 15 little cuts in here, right? Maybe another one there, another one there. Not at all even, but I could go through and go, okay, x0, x1, x2, x3, and so on, all the way up to x. So let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, x10. So there I cut it up into 10 pieces of different lengths. So this is just giving me a piece there, a piece there, a piece here, a piece there, a piece there, a piece there, and so on and so on. So I'm just trying to color code it to make it super clear what I'm talking about. I've just cut it up into these little intervals. They're each just little chunks, but they're not necessarily all the same width, and it's pretty hard to even see the stuff that's going on over there. But I've just cut up this whole thing into a lot of little pieces. Okay, so we're going to divide the interval AB into n subintervals, small intervals contained within it that make up the whole thing. And for now, let's not deal with this situation. Let's not deal with the situation where we have unequal length intervals. Let's just talk about the situation where you have equal length intervals. So n intervals of equal length. Naturally, the left endpoint will be x0. The lowest index, the lowest number appearing next to an x will be the left one, just like we've got right down here. And we're going to let b be the nth one. That is exactly the same as what we got down here. When we split it into two intervals, it went from x0 to x1, the midpoint, to x2, the right-hand endpoint. Okay, cool. So, as we can see from this example, I just split the whole interval's length in half each time. The length of each subinterval, which in this case, and here's some notation, we're going to denote by delta x. So that triangle there is a delta. It's a capital delta. Change in x somehow is what we're trying to say here. This is just historical convention to use a delta, a little triangle guy. Okay. So the length of each subinterval, we're going to denote by delta x, this little guy there. We can find this by dividing the length of the entire interval by n. So we're just dividing. So we take how long the whole interval is, and we split it into n chunks. That gives us n equally long pieces. So we can use this to partition the interval from a to b into subintervals to approximate the area under the curve. So this is what we were looking at before. This will lead us to the idea of a Riemann sum. Basically, the gist of it, if I can draw up here, is that if I split this guy a few times, maybe I'll use 4 subintervals, I'll get x0, x1, x2, x3, and x4. And if I split this guy up, I can somehow, one way or another, I can approximate the area under here by making boxes. Now the other piece of what I have to do is I have to figure out how the heck I want to make these boxes. So I'm going to try to use some different colors here. Actually, let me use a yellow. That is, I know how wide each box is, but how tall should each box be? This is kind of the last big question. I could pick sort of a lot of different points. Maybe I pick the right endpoint and draw over. If I do this each time, I'll get some boxes like this, and just to keep things distinct, I'll do every other box a different color here. So I'll get some boxes like this, and these are some pretty terrible boxes, but you see what I'm saying. We got some boxes, and we could approximate the area under the curve using these guys here, and we get something that's, it's all right. It's not perfect, but it's all right. Okay. All we're doing here, the only new notation is these xi's and subintervals as an idea. We're just going to rename everything. We could name it by the actual numbers in here, but boy, we'd have to keep track of a lot of numbers. The idea is just that we're renaming everything in terms of x with a number as a subscript as a way to uniformize our notation regardless of which interval we're talking about. That is, it doesn't matter if a is 10 and b is 100, or a is 1 and b is 1.02. I can still talk about these xi's in the same way. I can still just label things with these no matter what. If I'm splitting something into n intervals, a full interval into n subintervals, I'm just always going to label the cut points with the same labeling system, just to make things easy. So, the idea here is we take an interval and we split it into n subintervals of equal length. This will let us define a Riemann sum. Let's do it. Okay, definition 1, Riemann sums. So this is the first real definition we've got in this section. This is when the rubber meets the road and we're going to start to understand what's going on. Rubber meets the road. Fitting analogy given all the car metaphors we've been using. So we're going to suppose that f is a function which is defined on a closed interval from a to b, and we're going to divide that closed interval from a to b into n subintervals of equal length. And we're going to label that length delta x. So we've labeled the length delta x, we've got n pieces. Now if xk star we're going to say xk star, where the star is that little asterisk up top, is any point in the kth subinterval, that is, the interval from xk minus 1 up to xk, for k equals 1, 2, 3, 4, all the way up to n, where n is however many, as long as this even makes sense, basically, that's what we're saying. Then we're going to say that the sum of f of x1 star times delta x plus f of x2 star times delta x plus on and on and on and on, all the way up to f of xn star times delta x, we're going to say that this is a Riemann sum for f on AB. That is, this is just one. You can have lots of different Riemann sums. This is just one of them. And notice, I can rewrite this bad boy right here. Everything is getting multiplied by delta x. That is, if I split things like this a little bit, you can see that there's a delta x in each box. So really, I could just put that delta x at the end and just write f of x1 star plus f of x2 star plus dot 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 all the way up to f of xn star. And I could break it down just like this. I could factor delta x out if I wanted to. Let's draw a little picture and make sure we got the idea right. So here, basically what's going on is I've got a line. You could think of it like this, okay? I've got my A and I've got my B. And what I'm looking at is I'm looking at this little closed closed interval, right from A to B. What I'm going to do is I'm going to break this up into some pieces. So I'll label A as x0 and I'll label B as xn. Let's keep it concrete. Let's call this like x4. I don't know, why not? So if I've done this, then I'm going to have to split it into 1, 2, 3, 4 subintervals. And I'll label these guys x0, x1, x2, x3, all the way up to x4. It works pretty well. It's a pretty good labeling scheme. So this little chunk right here, this is the interval from x0 up to x1 with a square bracket if I'm keeping the endpoints. From here to here, this is x1 to x2. This guy here, x2 to x3. And lastly, x3 to x4. Kind of hard to draw this in. Maybe I should have chosen 3 intervals, but whatever. We got 4 subintervals. We've split the big interval from A to B into 4 little chunks. We've got them here. 1, 2, 3, 4. All right, so I'm going to do a little tiny bit of erasing, and then let's put in our xk stars. So the idea is that we could choose our xk stars however we really want to. We could pick any point as long as we pick one point in each one of these closed intervals. One in here, one in here, one in here, one in here. Okay, so let's do it. Let's just pick some at random. Maybe I pick one there, I pick one here, I pick this one to be all the way on x3, and then I pick this one to be just right there. So let's call this x. Okay, let's make sure we have the convention for naming right. So this is in the interval from x0 to x1. xk star is any point in the kth subinterval from xk minus 1 up to xk. So this would be x1 since it's in the interval from x0 up to x1. This guy would be x2 or x2 star. Sorry, all these guys have little stars. This would be x3 star, and this one over here would be x4 star. So I just picked a point in each subinterval. As long as I'm picking one point in each interval, then I'm good to go. I can just evaluate the function at each of these points and get a Riemann sum. What is the sum telling me? So to show that, I'm going to do just a little bit more drawing. And I'll even just grab this piece right here. So let's see, can I select this well? Maybe. Yeah, good enough. All right. So let me move this on down. and let's draw a little picture of what's going on. So, basic idea is that, and let me do a tiny bit of erasing just to make things super smooth looking. So I'm going to get rid of these xi's up here, and I'm going to rewrite them somewhere else. Or I don't even need to rewrite them for this. You guys can remember that they were there. You know, it's in that other picture we were just looking at. So let's just suppose we have the graph of our function somehow thrown in here. Let me put the y-axis in. Okay, so I got my y-axis, I got my x-axis. This is some little chunk of the x-axis from A to B. And now if I draw a function, maybe it's this guy, who knows? This is y equals f of x's graph. Then if I am just going over and up from each one of these guys, here's what's going on. Here's what I'm measuring. So before, as we talked about, what we needed was a way to select the heights. That's what the xk stars are doing. So when I'm grabbing each of these little boxes, I need a height. That's what this is giving me. And then I just fill it on in. So this guy's going to have that height. I'm just taking a box whose base is a subinterval and whose height is given by the output of the function at each of the xk stars. So, gist of it is that if I trace over from x1 star all the way over to the y-axis, I get out f of x1 star. As I've drawn the box right here, that's the height. That's the height. And so notice each of these intervals, each interval has a width of delta x. In this case, delta x would be given by b minus a, this length right here, all over 4, since I split it up into 4 pieces. So this area, let me do another color so it doesn't get too messy. This area is f of x1 star times delta x. That's the height, f of x1 star, and the width is delta x. So it's the area of this guy. Area of this guy right here, the next one, just f of x2 star times delta x. Same for each one. F of x3 star times delta x. And, oops, did that last one a little bit messy there. Oops, there we go. Oops. And finally, f of x4 star times delta x. A lot of writing. These are getting to be some messy pictures. But ultimately, what we've done is we've taken a curve and we've approximated its area using a bunch of rectangles. We know how to split up an interval into a bunch of chunks of equal length, or at least I hope we do, right? If you can't split up a little chunk into a bunch of pieces, oh boy. The part that makes it look a little bit confusing is that we have to pick the heights of our boxes. We know how to choose the length of the base for each box, but getting the height of each box is where all these x stars come in, xi stars. And just using our labeling scheme, here's where they're coming from. The xi star is in the ith subinterval. We cut the interval up into some number of pieces, k pieces, I pieces, whatever letter you want to use for a general number. And we chose a point in each one of these subintervals. Okay, this gives us a Riemann sum. Now there are a couple of really nice Riemann sums. That is, we could choose our xk stars, our heights, the points that are going to give us our heights, in a couple of nice and very uniform ways. We could do a left Riemann sum. This is when xk star is the left endpoint of the interval from xk minus 1 up to xk. That is, a left Riemann sum is when xk star is xk minus 1, the left endpoint. Okay, We could do the same thing and make a right Riemann sum where xk star is the right endpoint. That is, xk. Bam. And a midpoint Riemann sum, if we wanted to maybe even make things even trickier or something like that, a midpoint Riemann sum would be one where xk star is the midpoint. That is the point that's right in the middle. So that's when xk star is xk minus 1 over 2. So think of it like you got xk minus 1, xk, and right dead in the middle of this point, it is from this guy over by 1/2 of the full length. So I'll get this point right here, which is xk minus xk minus 1 over 2. So that's this little guy right here. Okay, cool. Let's see what we can do with these guys. Let's try an example. Let's take it from all this confusing and messy looking formalism to a specific example. And if this seems hard right now, once we do an example, you'll probably go, oh, okay. So let's try it out. Okay, so first example, example 1. Let's let R be the region bounded by the graph of f of x is sine of x and the x-axis between x equals 0 and x equals pi over 2. We're going to approximate the area of R using a left Riemann sum with 6 subintervals, and then we're going to approximate the area of R using a right Riemann sum with 6 subintervals as well. So before we just jump into the straight up math, let's draw ourselves a quick picture. All right. So I've got us a graph of sine of x here, and the gist of it is if we're going from 0 over here up to pi over 2, we're trying to approximate a certain area, and this is just going to be this area right in here. So we're trying to approximate this area. What is it going to be? All right, let's see what we can figure out. So we're approximating this area, and we're going to do it with 2 different types of Riemann sums. One of them a left Riemann sum and one of them a right Riemann sum. The pictures will be almost identical. So let's just grab this little chunk here, and let's do this with 2 pictures. Okay, much better. We cleaned things up a little bit. So I've got my left and my right Riemann sums. I've taken this thing, and let's draw the pictures for each of them. So if we're going for 6 subintervals, we're just going to split each of these guys into 6 pieces. It can be accomplished quite easily just by taking each piece and splitting it in half. There we go. Now we'll split yet again, and this will give us some more. We'll need to split a little bit differently. We'll need to split each of these guys into 3. And there we go. Perfect. So now I've got a bunch of different little points. I've got my x0 over at 0. Now I've got x1, x2, x3, x4, x5, and over here is x6, which is pi over 2. Same thing right over here, x0, x1, x2, x3, x4, x5, and x6, which is at pi over 2. So for the left Riemann sum, I'm taking the left endpoint to make my boxes. Let's pick a different color. Here, because x0 is 0, my first box will have 0 height. Then at x1, I'll just trace up from the left-hand endpoint of this interval, trace up to the graph, and over, trace up from x2. There's my next box. Okay. Now trace up from x2, over, up and over. There's my next box. All right, up from x3 and over, There's my next one. And we're just going to keep doing this. We're just going to make boxes from the left corner of each interval. So the top side touches the left corner, and they're all the same width. And I've got 6 of them. It doesn't look like it quite so much in this first picture because I have kind of a weird box going on. One of the boxes is a little strange. It's that box at the far end. It's this guy right down here. This has height 0. Okay, so one of the boxes is kind of like the trivial box, the box with no height, but the rest of them are all genuinely boxes. If I go on the other side, for right-hand Riemann sums, I just start at the opposite end. So I go here and I pick this guy, then I trace on over, and then I go up, bam, 1 box, and 2 boxes, and 3 boxes, and let's see, 4 boxes, 5 boxes, 6 boxes. There we go, and if I shade all of these bad boys in, you can see that one of these is an overestimate and one of them is an underestimate. Yeah? The left one is an underestimate. There's little edges that I'm not hitting, while in the right case, I have an overestimate. Let's highlight these guys. So over here, I'm missing some little chunks. Missing these little chunks in here. There's a very small little chunk up there you're not quite seeing. Missing this guy, missing pretty much all of that right down there. While on the other hand, for the right-hand Riemann sum, I'm missing these little chunks in any case as well. I'm a little bit overestimating what's going on. Okay, and so there we go. We very slightly are off in either one of them a little bit too big, one of them a little bit too small, but this is what we're trying to compute. One of them we're going to do is we're going to compute the area of all of these guys. This will be the left Riemann sum. And for the other one, we'll get the area of all these guys. So the left Riemann sum is equal to the area there, while the right Riemann sum is equal to this area here. All right, cool enough. Let's go and actually compute what we're finding now that we've got a good picture of it. Okay, so just like we drew up top, we're taking the interval from a to b, which in our case is from 0 to pi over 2, and we're splitting it into 6 subintervals. This means that the length of each subinterval, which we'll denote by delta x like we said before, is just going to be, as always, b minus a over n. So that's pi over 2 minus 0 over 6. So pi over 2 over 6, that's pi over 2 times 1/6, that's pi over 12. So delta x is pi over 12. If we want to find the left Riemann sum, we're going to set x1 star, x2 star, on and on up to x6 star, equal to the left endpoints of the 6 subintervals we get. The heights of the rectangles will then be f of xk star for each of the k's. So our left Riemann sum, which is just going to be, as always, the formula f of x1 star delta x plus f of x2 star delta x, on and on and on, but this is just the general formula. For our specific case, it looks way easier. So we start at sine of 0 pi over 12s times pi over 12, plus sine of 1 pi over 12 times pi over 12, plus sine of 2 pi over 12s times pi over 12, and on and on and on, all the way up to 5 pi over 12. So notice I'm just increasing by a pi over 12 every single time, and every single one of them is multiplied by a pi over 12. These are all just my delta x's, aren't they? It's just this guy right here. Run it through a calculator. We got computers for this. what you'll get at the end of the day is something approximately like 0.863. If we looked at the picture before, this seems maybe kind of reasonable. We had basically, we've got a little box, and the part of the sine curve that was in there looked a little bit like this. It was a little bit more than half of that box is the area under there. So this seems like maybe not quite the right amount, but good enough. It's a good approximation. So if we do the right Riemann sum, now we'll be using the right endpoints. So x1 star, x2 star, all the way up to x6 star will give us the heights of the rectangles via f of x k star for k is 1 up to 6. So same formula, we're just using different x1 stars, x2 stars, and so on. Instead of starting at 0, i.e. 0 pi over 12, and going over by a pi over 12 every time, now we'll start at pi over 12 and go over by a pi over 12 every time. So sine of pi over 12 times pi over 12 plus sine of 2 pi over 12 times pi over 12, and on all the way up to sine of 6 pi over 12 times pi over 12. This will give us something in the vicinity, if you punch it in a calculator, of something like 1.125. So notice, all we're doing here, where we're getting the values that we're plugging into sine, because I think that's probably the trickiest piece to figure out how to do, is we're just starting with 0 here, and then we go over by a pi over 12, and then we go over by another pi over 12 to 2 pi over 12, and we keep doing this again and again. We got 1, 2, 3, 4 right there, now 5, now 6. And so we'll get 3 pi over 12, 4 pi over 12, 5 pi over 12, 6 pi over 12. But in this case here, notice which ones we're selecting. We're starting with the left point. So we grab this guy, 1, 2, 3, 4, 5, 6, and we don't touch 6 pi over 12. Down in the right-hand Riemann sum, we're pretty much just doing exactly the same thing. And I'm not going to rewrite all these just to save us some time. What we're doing is we're starting at pi over 12, and we're going over yet again. So I guess I will write everything down again, just for clarity, because it doesn't take too long. So here, instead of starting with this left endpoint, you could think of it like we're starting with the right endpoint, and we get 1, 2, 3, 4, 5, 6, and 0 gets left out. So that's the only difference between left and right Riemann sums, which endpoint you leave out. Notice, if I look, I've got sine of pi over 12 times pi over 12 in the left Riemann sum, and I've got a sine of pi over 12 times pi over 12 in the right Riemann sum. If I go on through, I can see that I've got almost all of the same things, pretty much all of the way through. Between the two, got 2 pi over 12 times pi over 12, sine of 3 pi over 12 times pi over 12, sine of 4 pi over 12 times pi over 12, all the way up to sine of 5 pi over 12 times pi over 12. And the things that get left out between the two of them, one of them is the 6 pi over 12 times pi over 12 in the right Riemann sum. That's the right endpoint of the interval. In the left Riemann sum, I left out sine of 0 pi over 12, just sine of 0 times pi over 12. This is corresponding to the left side of the interval. So all the differences between left and right Riemann sums is whether you leave off the left or the right side. In a left Riemann sum, we have the left side, we leave off the right. In a right Riemann sum, we have the right side, we leave off the left. Pretty cool. So we'll get a lot better methods to deal with these soon, but I think that's probably about enough for now. Fun! what's up? My name's Aaron, spelled with 3 A's. I'm 21 and a half, I'm a free spirit, and I'm just looking for someone excellent to do some math with. If you had to know something about me, oh man, I guess my favorite mathematical object? Probably a scheme. I really love it when a sheaf is isomorphic to the spectrum of a commutative ring. Yeah, so if you think that this is right for you, then you just gotta give me a ring.